Lecture 15. Acids and Bases. Objectives. Explore two theoretical frameworks for acids and bases and examine the correlation between conjugate acid-base pairs. Understand what atheist strengths means. Understand the relationship between acid strengths and the strengths of the conjugate base. Learn about the ionization of water. Understand pH and pO. Learn to find pO and pH for various solutions. Learn to use a calculator in these calculations. Learn to calculate the pH of a solution of strong acids. Understand the generic characteristic of buffer solutions. Learn about the buffer solution in blood. Introduction. Acids are substances that increase the concentration of hydrogen ions, H, when dissolved in water or, more generally, donate protons in chemical reactions. Common acids include hydrochloric acid, HCl, and acetic acid, CH3COH. Acids typically have a sour taste, react with certain metals, and turn blue litmus paper red. Bases are substances that increase the concentration of hydroxide ions, OH, in aqueous solution or accept protons in chemical reactions. Examples include sodium hydroxide, NaOH, and ammonia, NH3. Bases often feel slippery, taste bitter, and turn red litmus paper blue. pH is a quantitative measure of the acidity or basicity of a solution. It is defined as the negative logarithm of the hydrogen ion concentration.
This is the formula for the pH. pH is minus log the concentration of the hydrogen ion. So the pH scale typically goes.
The pH scale typically ranges from 0 to 14, where values below 7 indicate acidic solutions, 7 represents a neutral solution, and values above 7 indicate basic solutions. 1. Two theoretical frameworks for acids and bases. 1.1 Arrhenius theory. An Arrhenius acid produces H, or H3O, in water. An Arrhenius base produces OH in water. Examples: HCl, AQ, H plus Cl. NaOH, AQ, Na plus OH. Small blue diamond limitation applies only to aqueous solutions. 1.2 Bronsted-Lowry theory. A Bronsted-Lowry acid is a proton, H, donor. A Bronsted-Lowry base is a proton, H, acceptor. Example:
Subíndice base.
Then ammonia plus water produces the ammonium cation and the hydroxide anion. In this case, the ammonia accepts one proton from water. So water in this case is a donor of protons, so it's considered an acid, while ammonia is accepting a proton and is the base. But if you go to the products, you can see that the ammonium ion give or release a proton to the hydroxide anion. So this is the acid, but as it is in the part of the products, we say that this is the conjugate acid. And this that is the acceptor is the conjugate base. Then this theory is broader and applies beyond water. Let's see here, conjugate acid-base pairs. Here we have hydrochloric is the acid and the conjugate base is the chloride. Ammonium is the acid because it's a donor of protons, and ammonia is the conjugate base. Water is an acid because it releases protons, and the OH negative, the hydroxide ion, is the acceptor, is the conjugate base.
Acid strength, not atheist strength. Acid strength refers to the extent of ionization in water. Strong acids ionize completely. Weak acids ionize partially. Common strong acids, memorize. HCl, HBr, HI. HNO3. H2SO4, first proton.
Yes, the first proton only in the sulfuric acid is considered as a strong acid. Let's see what is the relationship between acid strength and the conjugate base strength. Here we have a rule.
Key rule, very testable. The stronger the acid, the weaker its conjugate base. Examples. HCl, strong acid, Cl, very weak base. HF, weak acid, F, relatively stronger base. Small blue diamond strong acids have negligible conjugate bases. 5. Ionization of water, autoionization. Pure water ionizes slightly.
Then pure water is not completely ionized, it's only partially ionized, produces the hydronium ion and the hydroxide ion. At 25 Celsius degree, the concentration of the ions in solution is equal to 1.0 times 10 to negative 7 molar. Then the pH, as we have seen, pH is minus log the concentration of the hydronium, while the pOH is minus log the concentration of the hydroxide ion. The relationship between pH and pOH is that the sum of both at 25 Celsius degree is 14. So if we have the concentration of the ion, we can calculate the pH using this formula. Let me explain you something that will help you. When you have a product like this, it is equal to minus log what? The log of 1 times the log of 10 to minus 3. Then how we can solve this? We say, well, it is minus 3 plus the log of 1.0, that is this number. And the log of 1 is 0. So the pH, and as you have here a negative number, the pH will be positive 3. Then, as you can see, when you have 1 here, the pH is this number, but positive. If not, you have to calculate, for example, if it is 2.0 times 10 to negative 3, for example, you say that it will be 3 minus log of 2. You go to the calculator, you can find the log of 2, and then you subtract this result to 3. And this will be the pH. When you have given the pOH, you have the pOH, you can calculate the pH because you subtract 14 minus the pOH and you will get the pH. In the case of strong acid solutions, it's very easy to calculate the pH because it's minus log the concentration of the acid. All right, let's see the generic characteristic of a buffer solution. Let's go, what is a buffer solution?
Generic characteristics of buffer solutions. A buffer solution resists changes in pH, contains a weak acid and its conjugate base, or a weak base and its conjugate acid. How buffers work. Added acid is neutralized by the base. Added base is neutralized by the acid. How to prepare a buffer solution. 1. What a buffer is, quick reminder. A buffer solution resists changes in pH, contains a weak acid and its conjugate base, or a weak base and its conjugate acid. Examples. Acetic acid, CH3COH, plus sodium acetate, CH3SO. Ammonia, NH3, plus ammonium chloride, NH4Cl. 2. General strategy for preparing a buffer. 2 main methods. Method 1. Mix a weak acid with its salt. Most common in teaching labs. Method 2. Partially neutralize a weak acid or weak base, using a strong base or strong acid. 3. Method 1. Weak acid plus conjugate base salt. Example, acetic acid/acetate buffer. Step 1. Choose the buffer components. Weak acid, CH3COH. Conjugate base, CH3CO from CH3CO. Step 2. Decide the desired pH. The pH should be close to the pKa of the weak acid. For acetic acid,
P mayúscula K subíndice I casi igual a 4Q.
Yeah, the pKa is you can find this in the books in different tables, and these are characteristic for every acid. So the pH, according with the Henderson-Handel-Waage equation, the pH is the pKa plus the log of the concentration of the base divided by the concentration of the acid. Okay, what is important for me at this moment, because you're going to study the buffer solution in other level of chemistry, that buffers are very important because they resist addition of small quantities of acid or bases. The pH remain almost constant because of this combination of a weak acid and the conjugate base, or a weak base and the conjugate acid. And the other thing that I want you to understand is that the buffers are very important. For example, we have a buffer in blood, that is the carbonic acid bicarbonate. This system is the one that makes possible that the pH in blood remains almost constant around 7.4. Then when the pH is lower, we have acidosis. When the pH is higher, we have alkalosis. There are two problems of health, very serious in the human body. Well, now we are going to have some exercises. For example, you need to find the pH from the concentration OH. Then you say this is a concentration OH. Then you apply the log of the concentration of OH, and you get the pOH. In this case, is 5.20. These are the steps that you can follow in order to use the calculator in this kind of calculations. Well, that's all. I hope that you understand a little bit about pH, acids, and bases. That's all in this level of chemistry, and I hope that you have learned some chemistry with me. Thank you.